And one more example of graphing polynomials, and this is the f of x equals negative x squared times x plus 5 squared times x minus 3 squared, x minus 6. So the zeros, well, any factor of 0 will make this whole function 0. So when x is 0, it's going to be 0. When x is negative 5, it's going to be 0. When x is 3, it's going to be 0. When x is 6, it's going to be 0. So those are my zeros. And since I have a factor, if I put f of 0, if I put 0 here, the whole thing's going to be 0. So my origin is actually the intercept, 0, 0. So that's one of my zeros, and that's actually my y-intercept. You can see because it does cross the y-axis there, touches the y-axis. And x equals negative 5, there's a 0 there. X equals 3, there's a 0 there. And x equals 6, there's a 0 there. So we've got our intercept and our zeros all set. Now we need our end behavior model. So we just add up our exponents. So this could behave like x to the, that's going to be negative, pardon me, negative 1, 2, 3, 4, 5, 6, 7. So that's negative odd. So that's going to behave like y equals negative x squared. So that's the diagonal line that goes in the other direction, like this. That's our negative x. So it's going to be going like this, upper. If we go to the left, it's going to go to positive infinity. As we go to the right, it's going to go to negative infinity. So there's your end behavior. And let's just check our multiplicities. So over here at x squared, it's going to touch and return. Or at 0, I should say. At negative 5, it's going to, that's also going to be touch and return. And at 3, it's going to touch and return. Wow. And then it's going to finally cross at 6 to match our behavior. So that's all we have to do. So we can, so it comes like this, comes up. And I can assume the high point is going to be somewhere in between here. So I say about 2.5. So I can put it like this. That might change the contour of how I want this to come down, so I estimate. Although I don't know how high it goes, it could go really high, so that would change it. I just don't want to put that value in. It would actually be a fraction. So I'll just assume it's going to go like this and come up something like that. Comes back up here. They go like that. It's kind of almost like an out and back roller coaster, doesn't it? Call this an out and back where it goes out and comes back up. Looks like the high point should be probably between 1 and 2, just as an estimate. So I'll put maybe something like that. And looks like the low point might be between 4 and 5, so I gotta have it go like, oops, it's gonna touch and return at 3, pardon me. It's also got a touch and return, so it's gonna go like this. Maybe the high point would be between 4 and 5. And finally, down she goes. So something like this. Some of the original old roller coasters at Santa Monica were like this. They just had a lot of little dips in them. They would go down like that. They come up, go back down, dip. If you go into the history of roller coasters, you can see some of the early ones were just like this. That's what they call them, roller coasters. Coasted and you rolled. So there you go, something like that. So that's the best we can do unless we actually found the values here, and I don't want to put that in that expression. That'd be real difficult without a calculator. And this, we put an arrow there, arrow down there. Okay, so I think that should make sense. Take a look at that. That was nice when we had the y-intercept being 0 because that saved us a bit of work. Does that all make sense?